welcome back. Hello, hello, hello. This is going to be my last stream for the year. So welcome, thanks for tuning in. We're going to continue working on our little Asteroids clone in Haskell. And maybe we'll get to some other stuff, I don't know. We'll see. We'll see what happens. So I'm going to boot up my editor here and get our code going. So our current game currently looks like this. Let me bring the music down to just a smidge. All right, we can navigate our ship around here. We added bullet firing. Of course, things are super slow right now because I've got like a bazillion things booting up at once here, competing for memory. However, and also we're not running with compile optimization. So never mind the slowness right now. It's because of reasons. Everything on my computer is running slow right now. In fact, if you're watching this stream and it's looking good and sharp and crisp, awesome. Anyhow, so this is our game engine, our game right now with Asteroids. All we have to do is get the bullets firing in the right direction, and we'll get that working tonight. Cool, 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 cool. All right. Get our builder going, our compiler going. We'll set it to fast, which is no optimizations at all. File watch, so it just watches us for file changes and recompiles the game for us. Discord's booting up, which is probably why everything's running super slow. There we go. Hopefully it'll all settle itself down in a second. Okay. Got a little to-do file going with our updates. Got to fix the bullet physics. That's what we're going to work on. Okay, Asteroids. Game. This is our file here. Bunch of code. Good times. Bullet physics are down here. Let's see, Raptors, no, that's just some helper stuff. Render bullets, that's the rendering code. I think we just do it up here. Let's see. Update bullet physics, that's the function we want. So our equation here is no good. And we also don't want the position to be like beside the ship at that point. We want to account for the rotation of the ship and kind of point it at the right thing. So how do we do? How do we do? Rotation. This function rotates a point around some origin. So this is what we use. We use this rotate origin function to rotate all the points of the player's ship around the player's center point. So if we can get an initial offset of the point, I don't think we need this one, no. I think we need to look at my notes. I write stuff out, so you're like me, you journal everything you work on. So you can refer to stuff later when you learn things. Yeah, so we need to rotate. We do need to do a little bit of rotation off a constant here. Taking into account the player's current rotation. So the bullet data let's look at that. We have position, velocity, and rotation. So we're going to set the rotation as the player's rotation when we create the bullet, and we have to figure out the right position for it. I don't think we need to accelerate, we just need to force the bullet at a constant velocity. Which we'll get to. Small steps, baby steps. Let's just get it fired from the right position first. Okay, so when we go to fire a bullet, we create it here. Okay, so what we're going to do is we're going to have some constant factor offset that we want. I'm going to just hard code this right now. Say, I don't know, 70. Multiply that by the coast. Ooh, actually, yeah, we'll do it up here. Oh, the rotation that we want. Rot. And we'll add that to that. The X part of the position. Px and Py. We'll take the sine of the rotation, radians plus Py. And then position should be the V2 of the Bx and the By. Hopefully. Get rid of that. We don't actually use pause anywhere else, apparently. Oh yeah, because we constructed the pause from it, so we're just taking the components parts. Let's try that. Compile successfully. Let's see what it looks like. There, okay, so it's pointing out in front of us now by rotation, which is good. Now we just got to get the acceleration of the bullet going properly. Whee! Trippy. Okay. That's one problem solved. Let's make the factor a little bit smaller. I think the ship size is about 20. That should be a little bit ahead of the ship. Maybe a little too close. I should offset a little bit. Ooh, we gotta offset a little bit by the width of the bullet, however wide we're gonna render it. Because the SDL rects are rendered by the top left corner and and then the width and the height. So you can see it kind of coming off at a weird point there. We kind of want to be a little bit more towards the middle. I don't think we're actually going to render them as squares anyway, so we should account for that somewhere in our calculations here, but for now, this is good enough. We'll just make this like 25. Okay. Okay, boom, boom, boom. Cool. Sickness. Okie dokie. That's my Discord. Maybe later. We have a cool Discord channel, by the way. If you go up to declarative.tv there, you'll find the Declarative Programming Streams Discord. There's lots of good stuff there, including a channel for this channel, as well as others, where you can chat, discuss stuff, whenever you like. Show me your projects, show me what you're working on, that kind of thing. Cool. So, Let's create a commit for that. Bullet position. Fire bullet position. Fix the fire bullet position. The bullet position is offset from the player rotation. So that it appears in front the player ship. Excuse me. So that's that. Now, velocity acceleration. So when we're updating the bullet, we want to just move the bullet at a bang speed, constant speed. Okay. How do we set the bullet speed vector up? Let me look, let's look at our library, our linear library. See if there's anything in there for setting, like, vector magnitudes and stuff. Difference of vectors, linear interpolation between two. Sum of vectors. Negate it. Right scalar product, left scalar product. Division. Sum multiples. Produce a basis. Scaled. There's our unit vector. I don't need the outer tensors or anything like that. Let's see if I can search for what I'm looking for. Magnitude? No. Scalar multiplication? Multiply? I guess maybe it's with just numeric multiplication. Okay, maybe that's what that means with this. So let's do the same for that. I'm gonna rename bullet velocity to bullet speed. Velocity is probably fine, actually. Well, let's leave it at that. Okay. Let's compute a new vector for this as well. We're going to take the bx and the by of the position. That's our position. Px, by. And we want the vector difference. Like this, I think. B pause. B pause. Something like that. Hopefully that applies in the right order. Yes, I know I'm not using velocity right now. I'm hacking. Hacking around. We're still updating based on acceleration, I think. We'll fix the update to just consider the velocity. We update the bullet positions, yeah. Bullet velocity. And oop, sort of. Maybe way too much though. Let's try a smaller factor there. Mirror, mirror, mirror. Mirror, mirror. Okay, almost. So it's no longer, well, it's firing from the right position. Okay, but we have to change our velocity calculations, I think, when we create the bullet. Sort of. It's like firing out, right? But as our position changes, our bullets changes. And I think that's because how we're basing this off the position here. It's not a fixed amount that's changing over time, right? So that kind of makes sense. Let's put some fixed values in here. It's always going to go towards that one direction. Okay. So that part of the equation is like where we're aiming it. And if we put it at a constant, it aims at a particular point, right? Make this like 20. And it's going to aim at a different point on the screen. A little bit lower from that corner. That's on the Y direction, and this one controls the X. Okay. So now if we make it 100, it's going to be a little bit over more on the screen across. This way. Right? Wah. Kind of fun to play around with. Okay. So we do need to base this off of our position. Like our current position. This part controls the direction. Mm-hmm. Well, maybe we just take the parts from px and py, put cosine and sine on them as well. God, I haven't done this stuff in years, so trying to remember all the math is fun. Okay, so that's not it. Okay, let's do a little Googling. Asteroids, constant, bullets, speed vector. Or maybe we could just look up the math for it. Move a point along a vector, constant speed. Okay. So b minus a is, or b minus a, vector subtraction there, is a vector in the direction from a to b. Dividing by its length produces a unit vector in that direction, and multiplying by the presumably positive scalar u produces a vector of magnitude u in the direction from a to b, which is precisely what you want as the velocity vector. Perfect. Yes, that sounds like what I remember. Okie dokie. Move this back. And so our bullet velocity. We have to figure out what B and A are going to be. Right, so B will be the rotated point, and A will be our origin point, Px and Py. Yeah, so we'll do B pos. Yeah, B pos was right. Sorry, B pos, V2, Bx, By. B pos, yeah. Okay, we subtract out our original pos. And then we multiply it by a scalar, which produces a vector magnitude blah. So that's our magnitude about how fast out we want it to go. There we go. We just have to account for rotation. But otherwise, looking good. Dividing by its length produces a unit vector. Right, okay, dividing by its length. And then multiplying that. So to do something with this term, divided by its length, multiplying this by that, and then we should have it. Okay. Length. How do we get its length? Oh, we just can get the unit vector. Okay. A unit on X. Oh, it takes a setter. How does the vector, how does that function do it? Okay, interesting. No, don't need all that stuff. Okay, well, we have to get the length of the vector ourselves, I guess. Write that function. Length of vectory. Length of vector. Add the square of its components, then take the square root of the result. I guess we'll do floating. A, the v2 of A. And we get some value out of that. Alright, so we take the square root of its add the square of its components and take the square root of the result. Ooh, we can't do that with these. Do you want it to be 2.0s? Or you just, no, we don't have an instance for this operator? There we go. Okay, so we length. And then bullet. We take the length of this. Oh, it's going to collide with prelude, so we're going to import that qualify, maybe? AV? Asteroids vector? There we go. AV.length. And then we have a problem with clamp vector because we changed the import. And still got a type error here. Let's just fix that. I'm dividing by its length. Okay. Okay. So we want this value. I'm gonna call it foo for a second so I figure out what's happening here. So we want to take foo divided by the length of foo. Can't use that division. Can't use that division. We have a V2 division. We have equal ord1, read, fine, additive, foldable, generic, coalgebra. We do have a num instance on it. As long as we have a num instance on its component parts. Okay, so our division is entered a division here. We're dealing with floats. We take away the length from foo. Fractional, we should have the fractional division then. Oh, well, we want another V2 float on that side, that's why. So we need like a scalar division if that's what they mean. Or, because I didn't see a vector division operator in there. Oh, maybe we do have it. Ah, there we go. We have a special operator for it here. Dang. Okay, whoa. almost right. Now we can update our factor, and that should... Let's make it something conservative like 3 first. See if it starts going in the right direction. Oops, no, didn't want to do that. Hello. There we go. About right. Let's increase it a little more. Okay, bam, bam, bam. Yes, this is starting to look more like asteroids. A little bit. We just have to increase that speed a little more. This has got to be... They're currently launching, like, slower than the ship. Like, too slow. We're almost there. Do we have a bullet speed variable we can set, maybe? We'll do that in a second. So, like, 20... Let's try, like... 80, something ridiculous. There we go. Woo, much better. Nice. Okay, cool. It's looking good. Change it. We'll scale it back a little bit from 80 to make like maybe something 70. So who is like our unit vector? Or it's not the unit vector, but it's the... Is it? Direction vector. B direction. In fact, I might want to add this as a function to our little utility library for vectors as well. So I'm going to go over to linear vector, and yeah, we'll call it the velocity vector. And our input to the velocity vector is some v2a, and we get back a scalar a, no, a v2a. Our input's going to be the position vector and be pause. So a rotation. we're also going to need a float. Position, we'll put the float second. Yeah. And yeah. So what do? We're gonna take almost exactly the same code down here. Yeah, I don't know if I want to duplicate the rotation inside of here, actually. I think maybe we just want to take the vector. And I'm just going to take the V with a length of V. And we'll make the float amount. Yeah, we'll add the float amount in there. We'll multiply it by that. We'll call it magnitude. We'll just type the length there, so I mean this one. Hmm? Oh, this... What the... Hang on, yeah. This is literally this expression here, just with 70 replaced with V. Oh, I just have the order of the arguments flipped around. Oops. No, V is the vector, and magnitude is the magnitude. No, well, that's right. What the heck? V2 is V, A is the magnitude. Could be a float. You want this to be an int? I think this needs to be a V2 for some reason. Weird. Okay. Well, whatever. It's not that big of an improvement. If I find myself doing that a lot, I'll I'll make a function out of it, but for now it's fine the way it is. Okay. And I'll just add a little comment there to try and remind myself what that expression, what that formula means. Okay. Okay, so the next thing I want to do is I want to make the bullets wrap around on the torus as well. Let's commit this first. Excuse me. Actually, review our changes here. We can get rid of this hunk. Keep that. What's this warning here? Oh, that's the warning I don't care about right now. Need to do... Yeah, looks good. Let's create a commit. Bullet velocity vector. Okay, and let's make them wrap around using our wrap torus function. So we go to update the bullet physics. We'll take the position parts apart, I think. Or can we just pass position in? We can pass position in. And a size. Okay. Wrap torus, position, and the size of our bullets. I don't think we have a size on the bullet thing, so I think we're rendering them kind of like, what's that, about 20? No, maybe like 10. Okay, we have some unused parameters there, which we'll clean up. Cool. Bullet chaos. Mwahaha. Looking good. Let's do that. When apply this change, we'll wrap the bullet positions around the torus. Bullets go in one side, come out the other. Okay, let's do a little cleanup pass. So I'm gonna turn on my type errors. Let's see. Done one list. Okay, so we don't use velocity here, so let's get rid of that. I don't think we actually use the bullet acceleration in any calculation. Well, so we can get rid of that. We're not accelerating them, we're just launching them at a constant rate. And it caused a bunch of type errors by getting rid of it. So let's go fix those. Get rid of that. Get rid of that. Gone, gone, gone. Alright. Well, then we rerun it, and it should just work. As it was before, which is what I love about Haskell. One of the things I love about Haskell, and programming in it. Ruthless refactoring. Okay, so we got rid of those fields. That's good. Fire billets, we got rid of that. The unused parameters. We use bullet tick. I think we meant to use it. We do. Okay, yeah. Okay, so that's bullet velocity. Let's see. We got the bullet code, and do we use the rotation anywhere? No. We only really use the ship's rotation to set the initial direction vector for the bullet. So we can get rid of that too. Okay. Yeah, that's all I need for bullets for now. So let's clean up our commits here. I'm just going to rebase them all and switch them down. Reword that. Looks good. So we'll fix bullet physics. Bullets fire correctly from the front of ship. Move at a constant velocity in the direction they're fired. Wrap around the screen. Just format that nicely, and there we go. Nice. Okay, so next thing we need to figure out are the asteroids themselves. And then once we have the asteroids, we can do collision checking, explosions, and then we can add juice like particle effects and colors and sound and all of that stuff. Maybe we want to do sound earlier. I don't know. I feel like I enjoy a game more when I have like a little bit of sound involved. So I don't like to put sound off too much. At least effects. Music can wait, but sound effects I kind of like. I think we can maybe wait for that until we get the. Yeah, let's figure out how we can do asteroids. So an asteroid in Asteroids depends on your implementation, but are like little blobs that move around the screen. And typically in most games of Asteroids, you have like two sides. You got big asteroid and then smaller asteroids. You blow up the small asteroids, you get points. If you blow up a big asteroid, it splits off into smaller ones. So an asteroid, whether big or small, has direction to them and move at a constant velocity like our bullets. Usually much slower than the ship and all that sort of stuff, to kind of make them feel like they're bigger and heavier, that kind of thing. So I don't know if we want to like kind of maybe somewhat procedurally generate a polygon, or if we want to do like a fixed polygon. So we need... What would be nice is if we had a function that took a list of points and closed the loop on them for us. Kind of like how we render the ship points. And we draw all the lines. With SDL.drawLines, right? And the idea with this, let me get my pen out. My music player, already out. So the idea with this is that we would generate a number of points kind of around some origin and make them, we can stagger them a little bit. All right, to kind of give our asteroids like a little bit of a jaggedy look. And then this function will just take all that list of points and then we can render them however we want. So kind of like this. We'll have like our asteroid origin point. We'll draw that a little bigger in the middle here. And then maybe what we can start with is we can start with like, you know, if we generate 4 points, kind of draw them in a box away from the origin, and then mess with them a little bit. So maybe we'll actually like kind of move this one in a little bit, this one over a little bit, this one out a little bit, this one in a little bit, and then we'll draw the final lines between the kind of moved around points as our asteroid. So if I wanted to do, say, 6 points, all right, we do around an origin like this. We kind of generate as we can go. 2, 3. 1, 2, 3. mess them up a little bit. Move this one up here, this one out here, move this one a little bit on the x-axis. This one in here, this one out here, this one over this way, and then connect up those. When we render them, we should get like a jaggedy looking thing that we can render. So let's try something like that. So I want to give it an endpoint point, and then I want kind of these 6. I want an endpoint point and a number of points, and I want these kind of like regular laid out points based off of that origin. Or we can just go right into the randomness and just kind of do this all in one pass, in one function. But if we're going to do any kind of randomness, it means we have to build these in I/O. In the I/O monad. Because sampling a random, a pseudo-random number generator, or sampling something outside of our program is an effect. Like it has to go through I/O, right? So what I think is maybe when we start up the game, we'll generate a bunch of these, and then we'll just, when we're actually like running the game in our kind of pure code, we can like sample from it. We can just take the next one, and we'll just cycle through the list when we're generating a asteroid. We could do it that way. That way we just don't have to have like I/O in the middle of our beautiful game logic. All right, we can cycle the list around. Maybe we can even use a deck to do that, and that way we could just take the head and it'll be an O1 sort of thing, and then we can put the tail back, you know, kind of move it around like a circle kind of thing. And that would be nice. But let's mess around with that a little bit, some random generation type stuff. So let me go to my device and randomness in Haskell. Sample the system.random package, I think. Or the random package. Okay. There might be a way to do it in a pure function that's like sort of random looking. Actually, now that I think about it. And then we could just generate them on the fly, and but they'll all look somewhat the same, always. Yeah, never mind. And then thinking we could just generate a seed from it when we start up the game. Actually, that might work. If we use like a pseudo-random algorithm, it's kind of like a sort of random, like a Mersenne twister kind of thing. We could generate a seed at startup when we start up the game, and then yeah, and then we don't have to do all this extra nonsense about shuffling around pre-generated asteroids. We can just, it'll be a pure function to generate one. Gosh, Mersenne twisters. Let's see how hard this would be to do. It's not super hard if I remember correctly. Yeah. Okay, well, it's not trivial, but well, it's sort of trivial, I guess. Yeah, let's not implement this ourselves unless there's one already in Haskell. Of course, it's in the random package. Or no, it's in Mersin random. Interesting. Alright, okay, so we can just generate a bunch of doubles or floats or whatever, you know? And then we could just use those as our offset. So we don't need like super like precise randomness, right? We're not building cryptographic functions here or anything. But I don't know if this library has external dependencies that aren't maybe not portable. Should be good. Okay, let's give it a shot. Okay, so packages, boom. We'll do Mersin random tier 64. Like this. Okay, everything compiles and good. All right, let's start an asteroid module. No, let's do the random generation first. So let's add it to the game state. So we'll just get this as a a vector of floats or a deck of floats. Random points. I'm going to start with a deck of floats, and if we need to switch to vector because we don't actually use the deck, then we'll do that. I'm thinking I might just use the deck just for cycling through the vector. But we don't really need to use it that way. I think if we just use a vector and a pointer into our vector, we can just index into it. Then we would just need some kind of data structure for tracking the current state of where we're looking inside the random points. Let me draw this out. Alright, so if I just have a vector of pre-generated random numbers, and all I'm saying is that we have some stateful pointer into this thing, right? And then if I say like get me 5 points, right? 5 random points. It'll just increment this, return this one. All right, and then the pointer will be here. And this one, and the pointer will be here. And then return this one, and the pointer will be here. And this one. And it'll cons all these up into a list, and then give us a list back. All right, so it'll be... We pre-generate this vector of random numbers at the start of the game when we start up the game. And then we get this every time we sample from it to generate a... something. All right, we can just ask for some number of numbers out of this pre-generated list. And then we can get like 1, 5, 4, whatever. We just get the list. None. That kind of thing. And that way we can get like sort of pseudo-random polygon generation going for our asteroids. And just make them look a little more visually appealing and different. So let's make it a vector. Float. In fact, let's do the data structure thing so we can keep the pointer and the vector together. Pseudo-random. We'll make it a pseudo-random of A. So we'll have the pseudo-random values be a vector of A, and the pseudo-random index be an int. If we can keep that int to be a valid index into vector, that would be super cool. And this could be a pseudo-random of floats. Of course, if we add it to the game state, we need to add an initial value for it. Yeah. I know I feel like we could derive it, but this would be just fine to do it this way. Empty pseudo-random. Let's do that. That's just pseudo-random. I'm empty 0. Or vector v.empty. Let's store A to be storable. Ooh. I don't like that, but what are you gonna do? Yeah, here's what we're gonna do. I'm gonna change the prefix for v to vector storable, vs, and I'm not gonna import that up there. So we're gonna do a little refactoring here. And I'm gonna just save that for now. I'll come back to it in a second once this refactor is done. It's just name changing, fairly mechanical stuff. Yeah, I'm going to you. So this will be vs dot map. Vs dot vector. Vs from list. Reline all that. Okay. And then I could import qualified data.vector as v. Cool. Ooh, wait, before I do that, I'm just gonna take a commit of this. Hmm. Two commits. So we're add Emerson Lister dependency. Refactor vector. We'll import storable vectors. They're qualified. Yes. That'll work. Import qualify data.vector. As v. Move that up there. There. Just be nice and orderly. Okay. Okay. Pseudo-random stuff. Let's get back to it. That should be good. Game state random points. Random values. It's a pseudo-random floats. Okay, things we could do with the pseudo-random. Get a pseudo value. We can turn it as maybe A. So we'll pull apart our components. We could do that with record wildcards here, I think. It's going to be a while for me to remember how to type that. Pseudo-random, but okay. So actually we want to change pseudo-random. Alright, so this would be really maybe A and more pseudo-random. Almost looks like the state monad. Okay, so if we get a pseudo value out, we get maybe that value and then the new state of the pseudo-random generator. So we're going to need our vector operations here. Our indexing one, we should probably use safe. This one's unsafe. That one's safe. So when we get it, we want to index into that value, and then we want to increment the pointer. So we'll let the value be... What's the first argument? The vector? Yeah, pseudo... random values. Yeah, like that. What the heck? And pseudo-random index. Alright, then we return V and then something else for the new state, right? Pseudo-random A. So to construct the next state of the pseudo-random A, we need to increment the index by 1, wrapping around, so modulo the length of random values. I wonder if there's like a function already in vector for doing something like this. It's not too hard to write on our own, but just save us something, but maybe not. Okay. So what we'll do, yeah, we'll just do that as the formula. We'll do pseudo-random with pseudo-random value stays the same. But we increment pseudo-random index plus 1 modulo the I don't know if it's vector length or vector size of pseudo-random values. Or maybe it's length. Okay. So if we've done this properly, Let's write a test just to make sure. Describe pseudo-random. Technically, it should always return just. The index should always be inside the pseudo-random when you construct it with some values. All right. However, we'll just do an example. Or maybe, no, describe get pseudo value. Okay, so we have P be our pseudo-random. We'll construct it manually with the from list. And we'll just give it 2 values. Actually, we'll just use the smallest possible example. And the index 0. Import that. Import data.vector. We're going to need qualified. We might need to add this module as a dependency to the test suite. However, when we do this, we should get R1 get pseudo value on P, R2 get pseudo value from P, R3 get pseudo value from P. So if we, well, let's just write it out longhand. Do R1, R2, R3 should be just one, just one, just one. Oh, right, because they return the next state. So we'll have to write that out too. I think it should be just the same as P. Oh, we're missing an instance for... Oh, it's just defaulting, a warning. Okay, should be fine. Yeet. That should be good. Let's run the test. Test. Good. Right, so this is kind of like the minimal example that I'm mostly concerned with when using pseudo-random, is that the next state, the index can't escape. Right, so if we implemented this wrong and made this bad, right, we would be increasing this integer out of bounds. And this test is just showing that the integer is always going to be 0 because that's the only index we can get with our formula. Right, if we implemented that wrong, then this would fail. Right, if we didn't have the mod on here. Fail, 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 fail. You should fail now. And it does. Right. We expected the index to be 0, but it got to 1. Oh, in fact, we should probably... This test isn't quite sufficient enough, because we don't use p again in the calculation of 2. This is a better test. P prime. This should be P prime. Should be P prime prime. Should be P prime prime prime. Alright, then R2, R1, R2, R3. It'll all be just 1. Yeah, we're gonna have to repack the tuples back up just so I can have the test back in place. P prime prime, and the final state, P prime prime prime. Okay. So now we should have it. Oh, wait, we have a loop. Have a loop. Oh, yes, it's right here. There we go. Skadoosh. Okay, so the failure should be more like this. All right, 1, 2, 3. All right, the index is out of bounds. That should never happen. So if we implement this properly, which we did before, we'll just undo that, so we have the mod back in place. Now it should pass again. There we go. So the index never escapes. So long as we keep feeding in the next state back into pseudo-random value every time we want to sample it, right? So, this is looking a lot like using the state monad. If it gets a bit unwieldy, we might convert this loop to use that, just so that we use this properly. But it's okay to write these out as these functions like this and convert it later. Just get the gist across. So we can get a pseudo value, we can get several pseudo values. Get pseudo values. It takes an int, the number of values we want to get out from a pseudo-random of A. And then we get the list of A and pseudo-random of A. Oh, we're running low on time here. Oh no. Okay, let's try and finish this, and then we will have to do our polygon generation in the new year. Okay, so let's load our parts of the pseudo-random. Okay, so we know how to get out one value. Let v's. We know they're always going to be just as long as we use get pseudo value. But we have to feed back the pseudo random we get back from pseudo value back into pseudo value again in order to get the next state and to keep things cycling through. And we're going to just collect the results every time we do that. And then basically that means we can do, however we do that, we can collect those together. Probably using data.maybe, like from justs, or map maybes. What is it? Cat maybes. So cat maybes should be safe. Meaning that our test will be that if our input integer is 4, we should always get a list of 4 values out no matter what we do. So why don't we write that test first, just to make sure that we implement that properly. We're going to have to add this do back here. To add another describe block. So we're going to describe, we get pseudo values. But always return the requested number of elements. Something like that. So our initial pseudo-random. Can be a not so random list just for our test purposes. Maybe make it 1, 2. Starting at index 0. Now, our V's are function. If we call get pseudo values with 4 on P, we should get a tuple with a list of length 4. 1, 2, 1, 2. And our final state should not, let's see, that should go back down to 0 again. The index is going to go 0, 1, 0, 1. Oh, so it should end on 1. So it should be P where the pseudo-random index is equal to 1, I believe. Yeah. We'll turn on our test runner just to watch that as we go. Oh, right. N. Okay, so now we need to do something with cat maybes. I think we're going to have to do this recursively. So we're going to we're going to initialize with an empty list, and we're going to give it P. And then when that's done, we can return V's with something. No, we have to put our recursion on the outside. That's right. That's how we're going to do this. So we're going to accumulate values into here, our input parameter that we're going to give to go, and we're going to recur on P. We'll give them an order NP. So go is going to be our list of A, int pseudo-random A, to list tuple list of A pseudo-random A. Okay, so our termination list of A is going to be our accumulator, our accumulated list. Our termination condition for this recursion is going to be integer. So when the count equals 0, that's when we're going to return. So we're going to have to assume that int is greater than 0, otherwise this function won't work. Actually, if we give n in the last position, we could put a guard on that, which would probably be a little bit more clearer. Put it over here. Yeah, it doesn't really matter, I guess. So we want to guard this on when n is less than 0. Right, it doesn't, we can't return a negative number of pseudo values. We could, like, if I was doing this nice, I'm super proper, I might, like, return an error back, or an error condition, like, or an error value, like, or even maybe wrap this entire thing in a maybe, and this would be the nothing case if you try to give me invalid input. Here, I think if you're using it improperly, you're going to get junk data out. Just the empty list with our initial state untouched. There was like some laws of composition with this thing. This might not work, but I think it'll be fine. In the next case, n is greater than or equal to 0. All right, so we recur here. And otherwise, n is 0. So we're done accumulating, and we can return our result and our final p. Okay, so in this case, we're going to use get pseudo value. To get v and p prime. From our input. And then we'll recur with go and accumulate that value. So we'll recur v cons onto accumulator, and p prime will be our new pseudo-random value, and we'll decrement n. Oh yeah, that returns a maybe. Right, and yeah, we're going to have to transform the result of go, I think. That'll be a list of maybe a go return. And this function, right, just has to be, we can buy map over tuples. There might be a better suggestion for this that will come out of the linter. Import data.maybe for cat maybes. And then we just need, buy map. I think we get that from data.either. or something more general than that. Wait, data bifunctor. Let's Google it. Yeah, bifunctor. Data bifunctor. I'm sorry, and our accumulator type has to be maybe a. And yeah, we don't actually bind anything out here. So we can get rid of that. And just have some name shadowing stuff. So let's name this count and pseudo at the top level. Pseudo. Wonderful. Okay, did we implement it properly? We expected 1, 2, 1, 2. Pseudo-random this. Our pseudo-random index actually went out of range. So we broke our rule somewhere. I bet I know what it is too. Let's add another case here to get pseudo-random, just to get pseudo-rep value. The index range, longer list, a longer vector. So we have a pseudo-random read out from list 2, and our index starting at 0. You get R1 and P prime by applying get pseudo value from P, R2, P prime prime, get pseudo value P prime, and R3, prime prime, get pseudo value P prime prime. Okay. This R1, R2 with P prime prime, and R3 with P prime prime prime. Or prime 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 prime. Actually, we only really care about P prime 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 in this space here. We actually don't care about the results. All I care about is this final state of P prime prime prime. And I care about the index. So the pseudo random index of p prime prime prime. 3-tick. 3-tick p. Should be 0, 1, 0. But I got 2 failures. I got 3. So my mod equation's off. I don't know if I need the braces around it. I might be a little paranoid there, but hopefully that fixes it. A division by 0, right. Right. Okay. The reason why this is a problem. Let's imagine our indexing procedure here with a list. So to take our example, 1, 2. All right, so the length of v is 2. All right, so if we go 0, pseudo-random index is 0 plus 1. That makes it 1. Modulo. Length of v, 1. That should be a safe index, right? Right, 0, 1. That's cool. Okay, so our pseudo-random index is now 1. 1 modulo v dot length, or length of these. Oh, sorry, v. 1. Okay, that should be fine. Is it because I need parentheses around this? I wonder if this was like a precedence order error. I thought maybe I was the length needed to be decremented by 1 in order to get the right modulo for some reason, but okay. Okay. No, this should be, yeah, it should be 0, 1, 0, 1. Yeah, it should be 1. Okay, now we fixed it. Yeah, it was a precedence order issue. That's a sneaky bug, even for a language like Haskell. Right, so without this, the parentheses, I think what it was doing was taking the pseudo-random index and adding 1 plus modulo the v length pseudo-random, so it was growing past the bounds we actually wanted it to be, which was this number modulo the length of the thing. Okay, so now we only got the one error. This is not accumulating the values we expect. So let's get that. Interesting. Okay. So let's see. We should be accumulating a list of maybe A's. They're pseudo-random. So if our count n is less than 0, it should be the empty list in P. From our test code, we set it to 4, so that shouldn't hit that case off the bat. So n, it should hit this case. N is greater than or equal to 0. Alright, so we get out v and the next state of our pseudo-random by passing in the p we bind here. We get p prime. So we should be consing v onto the list, the empty list. And this should be just some, on our first iteration, it should be just one. At least that's what we're expecting. And then we decrement n, which initially is 4, by 1. So the next iteration, it should be 3, and accumulator should have just 1. Okay, I think we're going to need, I'm just going to need a little debug trace to see what's happening here. I think I understand. Debug. And we're going to debug.trace here. V is going to be show V. Show P prime. Oh, we don't have a show instance on it. Temporarily add show.
The dark veil of night descends.
I think we have to add it up here too.
Our order numbers have thrived in recent times. Finally, the time has come to unshackle the beast that mankind has feared for so long. Relinquish your fear and submit to the cause. You will find all you
Okay, so we got V.
The year is 1988.
Just 2, just 1, just 2, just 1. Okay, so that is recurring in those cases, the right number of cases we expected. Except we're getting one more. 2, 1, 2, 1. We're getting 1, 2, 3, 4, 5 recurrences here. we don't want the last occurrence. So it should be greater than 0. And then if it's equal to 0, that's the last case. Otherwise, and return the tuple of the accumulator and P. Maybe I should be appending onto the list, but I feel like consing should work there for some reason. I don't know. Okay, so we should show here the accumulated value. We should only see this line printed out in our debugger once. Okay, that's right. And it looks like we got just not quite the expected result values that we wanted. Interesting. So if I remove this debug.trace, we should get the same error, same test failure. Okay. So we're getting a 2121 because we're... Why is that? We're expecting 1212. So expecting to get whatever's v at index 0 initially. But get pseudo value is returning the next value. Not quite what we want for get pseudo value. We wanted to get the value at the current index and the next state of the index plus 1. I don't think I initialized it incorrectly. Like it's still index 0 here. So when we first go into get pseudo value and get pseudo values, this should be returning just 1. And we do 2, 1, 2. Oh, because we're consing on. It's in the right order backwards. It's just backwards. Okay. Yeah. So that was what I was thinking was we shouldn't be consing. We should maybe be appending. So that should be an easy fix. And this will polish off this function. Alright, so this would be append with the... Not super nice, but... Yeah, and then 0. Okay. So that's not going to be super, like, it's not going to be very efficient to do it like this. Yeah, it's not going to be the worst either. Concatenate should be straightforward for liths. I think. Ah. Right? Well. We're good there, at least. That should be fine. For some reason, it's not coming to my mind. Not Python, just in general. I think linked lists. They're linked lists. It depends on how Haskell and GHC implements them, I guess. But probably big O1. So constant. Okay, so probably not that bad, maybe. We're doing this kind of one at a time, so we're also constructing a new linked list node here to get the V's, so like we could use a more, if we're really concerned about it, a different data structure here, but otherwise, for a first pass, should be fine, and we're not going to be selecting huge lists here, at least in our game, so not too worried about it. Okay. So that's our pseudo value stuff, right? So now that we can construct a pseudo-random, well, we'll need a constructor for it. We can make just an empty pseudo-random. We can get a value, we can get a list of values, and now we should be able to get a random-ish pseudo-random, and to be able to construct our kind of somewhat random-looking asteroids. So, however, we're running a little over time this week, and this is the last stream of the year. So thanks for tuning in. Thanks for watching. Thanks everyone who's been watching all year. And we'll see you in the new year. So may all your monads be free. May your types always check. May you have a great holiday. Whatever you're celebrating. And we'll see you in the new year. So make sure to click follow, subscribe, all that sort of stuff to get notifications here on Twitch, or if you're on YouTube, you know what to do there. Follow me on socials. I'm Agent Ultra. You can find the code for this project at Agent Ultra on GitHub. I'm just going to create the commit here and push it up and show you where that is. So we'll do this, and this will add a pseudo-random. Data structure for holding a bunch of values and getting one or more out faithfully. Looks sort of random. If you fill it with good distribution of data. Okay, so let's push that up and show you where the repo is. It's on GitHub. Agent Ultra. Asteroids, that's our little Asteroids clone built in Haskell that we've been working on for the past 5 weeks or so, and you can get it here. I'm also on types.pl at Agent Ultra, and elsewhere. So there you go. We're also on the Discord, so go to declarative.tv and follow us there, and keep in touch on the Discord channel, and see you around. Peace out.